All right, hello, Math 201. We're here to talk about section 2.5, limits at infinity. And so this is to not be confused with infinite limits. Limits at infinity mean what happens as you go to infinity in the x, not in the y. And so when we say limit at infinity, this one means x is going to infinity plus or minus infinity, I guess. So a limit at infinity is x going to plus or minus infinity. Infinite limit is the limit as x goes to a of f of x equals plus or minus infinity. So that's an infinite. So an infinite limit is where the function is going to plus or minus infinity. So the y value is going to plus or minus infinity. A limit at infinity means the x value is going to plus or minus infinity. So that's the nomenclature, the kind of naming how we do it. So the idea is that if we go off to infinity, what's kind of the long-term behavior of our function? So this one, graphically, it's getting really close to this limit. And these limits are called horizontal asymptotes, these things that are that they're getting asymptotically close to. So that one's the one as we go to positive infinity. As we go to negative infinity, it's this m. And so those are called horizontal asymptotes. And by definition, these are one-sided limits. So limits at infinity, or the limit as x approaches infinity of f of x equals a number. If as it goes all the way to the right, it will go to that number L. And these are one-sided limits. So let's do an example. So what's the limit as x approaches infinity of 1 over x? Well, this equals, in a sense, or implies that it's 1 over infinity. But what is 1 over infinity? What does that mean? And so the way we can think about that, so it's 1 over a very large number. So 1 over a very large number. So like maybe 1 over a million. So 1 over a million. So that's really small, right? That's pretty close to 0. And then if you do 1 over a billion, so 10 to the like 9th or something, that's even closer to 0. And so they get closer and closer to 0. And so 1 over infinity actually is going to equal 0. And it actually doesn't matter which way we approach infinity. When you have a constant, so the key idea here is if you have a constant over plus or minus infinity, it's going to go to 0 no matter what, whatever the constant is, whatever. And so we're going to use that idea for limits all the time. So whenever you have the bottom getting really big and the top is kind of constant in a kind of comparison, then the limit will go to 0. And so let's do an example using that fact. And so by the sum law, this is the limit as x approaches infinity of 2. Well, you plug in infinity, that's just 2, plus the limit as x approaches infinity of 1 over x cubed. But that's just equal to 2, and then plugging in infinity, 1 over infinity. But infinity cubed is just infinity, right? It's still positive infinity. And so this is 2 plus 1 over infinity, which is 2 plus 0. And so that's equal to 2. So this is what happens when we plug in infinity and we get that. And so the idea of plugging in infinity is really the same. The algebra is basically the same. The main kicker is that when you plug in infinity and you have a constant on top, it just goes to 0. And so that's going to be the main thing we're going to use for this first part. Now, what happens if you have infinity on top? What kind of goes on there? And so these are called infinite limits at infinity. And so it's what happens when you're not approaching a number, but you're instead approaching infinity. And so infinite limits at infinity, there's really 4 ways you can do it. You can go up and to the right. You can go down and to the right. You can go to the left and up, or you can go down and to the left. And those are the 4 kind of ways I've written here. And so if the limit as you approach x from the right equals infinity, that's this one. If as you're going off to the right, it goes down, that's this one. If you go to negative infinity, it's positive, that's that one. And if you go to negative infinity, it's negative, that's this one. And so those are the 4 kind of cases. And this is called end behavior. So end behavior is what's happening as you move really far to the right or really far to the left. And so the limit as x approaches infinity of f of x and the limit as x approaches negative infinity of f of x, those are called end behaviors of a function. An end behavior can be a number, right? It could be a horizontal asymptote, or it could be plus or minus infinity, but it could also oscillate. And so it doesn't have to be plus or minus infinity. It could just not exist. In particular, the end behavior for polynomials x to the n, we know. If x is positive, the end behavior is no matter which way you go to infinity, either to the right or to the left, it always goes up. And so the limit is always positive. But if the polynomial is to an odd power, we notice that as you go up into the right, it's positive. But because when you cube or raise to the fifth power, or raise to an odd power, a negative number, it stays negative. When you move to the left, it's going to go down to negative infinity. And so we get two different types of limits. And so these are the end behaviors of certain polynomials. And we can actually use these to tell us what the end behavior is of any polynomial. And so here's the idea, limits of infinities of powers of polynomials. This is the key idea right here. That if you want to take the limit as you're going to infinity of any polynomial, just take the limit of the lead coefficient. And then if this is even or odd, we know what's kind of happening. And so I'm not really sure what I wrote here, but so here's an example. And so the idea is I want to take the limit as x goes to plus or minus infinity for the following two polynomials, that polynomial and that polynomial. Also, this is really hard to read, so let me actually rewrite this. So for p of x, and let's call q of x equal to, what was it? Negative 10x to the fourth, 3x squared plus 2. Negative 10x to the fourth plus 3x squared plus 2. And so the thing that you're not going to do is we're not going to use the limit laws on that and try plugging infinity into it, because that's just too much work. Instead, what we're going to do is to take this limit, the limit as x approaches infinity of p of x, which is this polynomial right here. We're just going to look at the leading term, which is the highest power x. And so we take the limit of that. We can pull out the -2 because it's just a constant, and then just take the limit as x goes to infinity of that. But then you get -2 times infinity. Infinity is, infinity is a really big positive number. And if we multiply it by a negative, it becomes a really big negative number. And so it becomes negative infinity. Similarly, if we take the limit as x goes to negative infinity of that polynomial right there, that just is the limit as x goes to negative infinity of that guy. Again, using just kind of pulling out the constants, you get -2 times. And because we're plugging in negative infinity right here and we're cubing it, it stays negative. And so it becomes negative times negative. So it becomes positive infinity. Finally, we can do the same thing with q of x. So maybe I'll even say this. So this is the limit as x approaches negative infinity of p of x. That's that one. And then this is the limit as x approaches infinity of p of x. That's that one. And then finally, this is the limit as x approaches infinity of q of x. But remember, that's this polynomial up here, I wrote it. And then now we just talk about the leading term, right? By this theorem, it's just the leading term. So it does what that guy's doing. And then you just pull the constant out, and then it's the limit as x approaches infinity of that. But infinity to the fourth power is still just infinity. So it's -10 times infinity, which is negative infinity. If we do the same argument over here, maybe I'll even write this out. This is going to be -10. And now it's going to be negative infinity to the fourth power. But negative infinity to the fourth power is positive infinity. So this is -10 times infinity. And that's just going to be negative infinity. And so the positive and minus both go to the same thing because it's an even powered polynomial. So it's going to do something like that. Okay, so that's how we use that. How about end behavior of rational functions? To do the end behavior of rational functions, the key step is to divide each term by the highest power in the denominator. And so whatever the highest power appearing in the denominator is, we're going to divide that so that the bottom will go to a constant, and then the top we'll kind of see what happens there. So for this one, the highest power is an x squared. So we divide every single term by x squared. And if you do that algebra, you get 3 over x plus 2 over x squared, and then 1 plus 2 over x. Now we plug in infinity. That goes to 0. That goes to 0, 0. So to 0, to 0. That goes to 0. And what we're left with is 0 plus 0 over 1 plus 0, which is just 0. And so that allows us to compute it really easy. Let's try another one. So what is the highest power showing up? It's x cubed. And so this is the limit as x approaches negative infinity, dividing every term by x cubed plus 3x squared over x cubed plus 2x over x cubed plus 2 over x cubed all over negative 2 x cubed over x cubed plus 6 over x cubed. Now, if we simplify that, that's the limit as x approaches negative infinity of 4 plus 3 over x plus 2 over x squared plus 2 over x cubed. And then over negative 2, and then plus 6 over x cubed. And so now we can just plug in infinity, or negative infinity, I should say. That will go to 0, that goes to 0, that goes to 0, that goes to 0. And so this just equals 4 over negative 2, which is negative 2. And so that will be the end behavior for this guy. So it will have a horizontal asymptote. Whoops. Sorry about that. So he'll have a horizontal asymptote at negative 2. And let's do one more example. So what happens here if we plug in infinity? Well, let's divide everything by x. So this is going to be the limit as x approaches infinity of 2x plus 4 over x over, and then 1 plus 3 over x. So if we divide every term by x, so times 1 over x, and then 1 over x. So that's what we did. We divided everybody by 1 over x. Maybe I'll do that in a different color. So times 1 over x times 1 over x. What does that equal? And so now what does that give us? Well, that will give us infinity. This goes to 0, 0, 0. And so we get infinity plus 0 over 1 plus 0. But that's just infinity over 1. But infinity over a constant, that's just going to be infinity. And so in general, maybe I'll kind of frame this a little bit higher. So this is kind of the key algebra for when you have infinity over a constant. So if c is a positive constant and you divide infinity by a constant, it's the same thing as kind of multiplying by a constant. And so you get infinities in those cases. And so that's the idea when you take infinity and divide it by a constant. It's the same thing as multiplying it by a constant. And so it doesn't affect that it's infinity. All that matters is the sign. Finally, I think I have a couple more examples, but let's talk about end behavior of algebraic functions. Algebraic functions are ones that have roots. So they're not just polynomials or polynomials over polynomials. They're ones that have roots. And so let's take the limit as x goes to infinity of this guy. And so what the highest power in the denominator is it's this, right? That's the highest power in the denominator. But what is the square root of x to the 6? Well, because x is positive, right? We're dealing with positive things. This is really just equal to x cubed. And so we can divide everyone by x cubed. And so this limit becomes the limit as x approaches infinity of 10x cubed over x cubed minus 3x squared over x cubed plus 8 over x cubed. And then on the bottom, we're going to replace it with that because these are equivalent when x is positive. But we can replace that and divide everything by square root of x to the 6 to bring it in. And so that will be the square root of 25x to the 6th over x to the 6th plus x to the 4th over x to the 6th, and then plus 2 over x to the 6th. And then we'll notice a lot of things are going to go to 0. Those guys cancel. Those guys cancel. That goes to 0. That goes to 0. Goes to 0. Goes to 0 when we take the limit. And so what is this going to become? This is going to become 10 over, and then the square root of 25. And so this is going to be 10 over 5, which is equal to 2. And so that limit, the horizontal asymptote for this guy, will actually be 2. All right. And let's talk about end behavior of transcendental functions. And so these are functions like e to the x, natural log of x, and all the trig functions. And so right now we'll focus just on e to the x and ln of x. And we have the following rules for e to the x and ln of x up here. And the way you can get those by looking at the graphs, right? Here's e to the x. As we go to positive infinity, it goes to positive infinity. As we go to negative infinity, it goes to 0. And then if you take e to the minus x, which is just flipping it along the y-axis, if you go to negative infinity, it goes to infinity. If you go to positive infinity, it will go to 0. Similarly, the way we can get the end behavior for ln of x, because ln of x is just the reflection over the line y equals x. As ln of x goes to infinity, it goes to infinity. As x goes to 0 from the right, because actually ln of x does not exist for negative numbers, ln only works for positive numbers, it will go to negative infinity. And so we can use that to calculate compute limits like this. And so this is just negative. The limit as x goes to negative infinity b to the minus x, but that's just negative infinity, because if you plug in negative infinity up here, you get double negative, which is e to the infinity. So it's just positive infinity. But then because we're taking the negative of that, that's why it's negative infinity. Similarly, we can do ones like this. Sorry, I wrote some laws that I'm not that specific anymore. If I want to do this one, I can split it up into 2 limits. To do the limit of this guy, I can pull out the constant and then take the limit as 0 goes to the right. But I have the rule right here that as we approach 0 from the right, it's going to negative infinity. So that's why that's negative infinity right there. And then the limit as x approaches 0 from the right of x squared. Well, you can just plug in 0 because it's a polynomial. So it's 0. And then you have -3 times negative infinity. So it just becomes infinity. And so this limit as we approach 0 from the right for that function will just be infinity. And finally, let's take a look at a trig function. The way we're going to do this is by looking at its graph. And so hopefully you remember what sine of x looks like, how it kind of has this oscillating pattern to it. And so because it's always oscillating, the limit will actually never approach one number. And so because it's not a number, we say the limit as x approaches infinity of sine of x does not exist. Similarly, the limit as x approaches, and it's true for plus or minus infinity, this is actually plus or minus, cosine of x, this also does not exist for the same reasons. And so that's kind of what happens with those guys. And for other trig functions, we'll talk about those later. All right, we'll leave it there.